Hi folks, and welcome back to Physics with Captain Rod. All right, I'm going to take a look at an example here, which is number 78 in your University Physics OER textbook here. And the problem we're going to look at is, imagine we got this long straight wire, carries a downward current. Over on the left here we have some sort of, I call it a bar, a metal bar of length A here. It's got a velocity vector that points down, so this bar is physically moving downward. Right hand side, distance b from the current. And what we're going to do is we're going to try to come up with an expression for the EMF induced in the bar due to its motion in a magnetic field. Now one thing I'd like to do is comment about the term EMF. Remember that stands for electromotive force, EMF. This is a term that I personally find very distasteful, I guess, because EMF is a voltage, not a force. It's the potential difference in that we're going to get from one end of the bar to the other, which is induced because of the charge shift we get because of them moving through a magnetic field. All right, now there's a couple different ways to handle this. Method number one here, we could talk about magnetic flux and Faraday's law of induction, which says that the induced voltage is the time rate of change of magnetic flux. A lot of times it's written with a minus sign, and that just has to do with the polarity of the voltage, which we usually use lenses for. I'm just going to leave it off for now and say magnitude of the voltage is equal to this. The other way we can handle this is just by looking at a free body diagram of a charge carrier, either a plus or a minus, in the bar. Now, either of these starts will get us where we're going to go. I'm going to talk a little bit about how we would set it up like this. However, my preferred method for dealing with problems like this is the one on the right. But let's chat about this guy for a moment. What we would do if we want to use the idea of changing magnetic flux is we would look at an area here. I'm going to kind of extend this. We look like some sort of area that looks like this, where we might call like this distance y and maybe this distance x or something, or maybe length times width. And we would write an expression for the magnetic flux through this area as it varies with current, and then we would take the time derivative of it, noting that in this example, the way I've set this up, the velocity is equal to dy dt. That would be one approach. I'm going to take, again, a slightly different approach. See how many of these I can get rid of here. Oh, it looks like all of them. And what I'm going to do is I'm going to look at a single charge carrier in this metal. Now, it doesn't matter if you look at protons or electrons. I'm going to imagine looking at a positive charge carrier. So I'm going to imagine a single positive charge carrier in here, imagining it free to move. And this charge carrier is moving down with a velocity v, and it's moving through a magnetic field. Now the magnetic field is coming from over on the right here, from this current. Remember that the field lines are round wires. They're circular. So I'm just going to draw some of the field lines. Okay. And you tell which way by right-hand rule. This is a little hard to do on the screen, but right now just kind of take your right hand, just kind of pretend like you're grabbing the wire with your thumb in the direction of the current. Your fingers will roll around in the direction of the magnetic field lines. So those field lines are going this way. That means over in the plane here, the magnetic field vectors are in the minus k direction. I'm going to go ahead and draw some of those vectors here. Oops. And also, by the way, the field varies in intensity. As we get closer to the bar here, the field would be getting stronger and stronger and stronger. So these are supposed to represent some magnetic field vectors minus k direction. In general, the magnetic field, due to a long straight wire, is mu sub O over 2 pi I over r. Now, in this example, I'm looking at that one single charge carrier. It got kind of covered up by my magnetic field vector. The R we're going to need is from that charge carrier to the wire, and we'll get to that in a minute. Now, again, free body of that single plus. I'm going to put this we'll put that over here. So here is that charge carrier, this one right here. It's moving down with a velocity v in this magnetic field. Now this is a little tough to do in this computer screen, but if you've watched any of my videos or other people's videos on how to apply right-hand rule, take your right hand, put your fingers parallel to the velocity vector, and you need to be able to sweep towards the magnetic field, which is in the minus k direction. Or another way to explain this, your palm should be facing in the minus k direction in a standard, what I call a standard x, y, z coordinate system. So when you apply the right hand rule, your fingers should be pointing down, your palm should be facing right into the screen, your thumb should be pointing left if you're doing that correctly. So the magnetic force on this particle is to the right. I'm going to go ahead and put a force vector in. And that force vector is calculated by taking QV cross B, which is QVB, sine of the angle between the V and the B. The velocity vector's down, that's minus j direction in my coordinate system I'm using. The magnetic field vectors are in the minus k, angle between them is 90, sine of 90 is 1. So any positive charge is going to be pushed basically to the right in this picture. That's going to give us a charge configuration that looks kind of like this. We're going to get a positive charge on one end, negative charge on the other. Now, what's happening here is this is a charge shift. It's not like any sort of, like an electron doesn't get from the right end all the way to the left. What happens is all the electrons in this metal shift to the left, probably a couple atoms or so. In the middle, there's really no net change in charge, but on the end there is. There's a region here that didn't have electrons before, now it does. And over here on the right, there's a region that had electrons and now it doesn't, leaving it positively charged. Now, plus, minus. Now we're going to have electric fields that point this way. Whoops, let me draw that so we can read it. In the metal itself, because electric fields always point away from pluses. I drew it outside the bar. It's important to realize that I'm talking about this would actually be in the metal itself. I'll go ahead and leave it right there now. And because we have an electric field, now we have a potential difference between the right and left end of the bar. Now, again, getting back to my positive charge, which I'm imagining somewhere in the middle, this electric field will now put a force on that positive charge, and that force is to the left. And that force vector is going to equal charge of the particle I'm looking at times the electric field strength. Now, electrons, remember, are the actual charge carriers that move in this problem. And the mass of an electron, order of magnitude, is around 10 to the minus 30th kilograms. Okay, so what that means is that if you put a force on an electron, even if that force is like 10 to the negative 20th newtons, you get accelerations of like 10 to the 10th meter per second squared. Long story short, the electrons, they shift. That shift happens instantaneously, and basically we have a force equilibrium problem again. That means that this charge carrier here is in some sort of equilibrium and the net force is 0, which is going to allow me to say sum of all forces equals 0. I'll go ahead and just do right positive. So we've got this force, QVB, right, and then this one is to the left, so I'll put minus Q times E equals 0. So the electric field, it's pretty easily calculated, is equal to the velocity times the magnetic field strength. Now, you might be tempted to say, okay, well then the potential difference is just E times D and multiply by, this distance here, the length of the bar that we called A. The problem is this equation is true only if that electric field is constant. And if you look carefully here, this magnetic field varies with location in this problem. In fact, it's the field around a long straight wire. So we can write mu sub O over 2 pi I over r being the distance. And I think what I'm going to do is I'm going to call that distance x. And now I'm going to define a variable that starts at my charge carrier, wherever that is, to the current. So now the potential difference, we're going to look at it on a small scale here. I'll put dV, difference in potential, is E dot ds in general, In this particular problem, I'm just going to put this. That's equal to velocity times mu sub o over 2 pi I over x, right? This gives the electric field times a distance dx. This would now change. This would now give us the change in electric potential, and that electric potential is dropping as we move right to left. Total difference in potential then we will get by adding these all up. I'll bring that minus sign out in front. Then I'll put velocity times mu sub o times I over 2 pi, and what I'm doing right now is I'm grouping together anything that's constant, and then we just have dx over x. Now this integral is going to be integrated along this path, starting at the right hand side of the bar and moving to the left hand side of the bar. So that's going to be starting at b and then integrating to a value a plus b. So this expression now is going to give us the potential difference, I should put a delta v here, between the right and left hand side of the bar. The minus sign is because if I integrate from right to left, the potential differences are negative. All right, anything constant can come out in front. And then the integral of 1 over x dx is logarithmic. That's a natural log function. That's going to be natural log x, evaluated from a to a plus b. Now, where we put the minus sign, it doesn't really matter. In this particular one, I would just advise we just leave it out front. So we're going to have minus v times mu sub o times I over 2 pi times the natural log of a plus b over a by time we evaluate these limits. And there's a property that I'm using, and when we evaluate the limits, that'd be natural log of this minus natural log of this, all right? But by properties of logarithms, that's the natural log of the ratio. So there's an expression for the voltage difference between the right hand side and the left hand side of this little bar here. I hope that this video describes this process reasonably well for you. Have a great day.